In certain instances, you may want to set up an annuity such that you have a desired accumulated amount at some future date. To achieve this desired accumulated amount or the future value, you need to calculate the present value of an annuity. This is the formula for the present value of an annuity. A represents the present value. R represents the value of each regular payment. N represents the total number of payments. And I represents the interest rate per conversion period. To derive the formula for the present value of an annuity, one may argue as follows. The amount P invested now and earning interest at the rate of I per period will have this accumulated value at the end of N periods. But this also has to be equivalent to the future value of an annuity S. So since this S represents the same amount as this S, then we can set the right-hand portion of each one of the equations together, like this. Okay? Now let's manipulate this equation algebraically. The goal is to solve for P. If we take this equation and we multiply both sides by the quantity 1 plus I to the power of negative n, we have one on this side and we have one on this side. Okay, there it is. Now, remember from algebra, when you have equivalent bases, all you have to do is add the exponents. So n plus a negative n is equivalent to 0. So 1 plus I now has a power of 0. On the right-hand side, this is distributed with each item inside the brackets. So you have 1 plus I to the power of n times 1 plus I to the power of negative n, that's this right here, minus 1 times that quantity gives you this part right here. Okay? And again, you have two items here with the same base, so you add the exponents. So that exponent is 0. Okay? And this stays the same. Okay? And then also remember from algebra that anything to the power of 0 is equivalent to 1. So right here, we have P times 1. This is all equivalent to 1. So P times 1 is equal to P. Okay, and this right here is equivalent to 1. Okay, and then just simplify this a little bit and you have this. Okay, and there you have it. Here is the formula for the present value of an annuity. Now notice, by the way, that the P changed to an A, and that is because our book's author prefers to use the variable A to represent the present value in this chapter. Okay, so A is going to represent the present value. R represents the value of each regular payment. N represents the number of payments. And I represents the interest rate per conversion period. Okay, if you use the tables, which you can, you would use this little formula right here, and you would look up a certain number on the table, okay, and multiply by the regular payments, and you would again have the present value. So you can use the tables or you can use the formula, and the result is the same. Let's look at some applications. Read example 1. Okay. So to find the present value, I'm going to do this using the formula. I'm also going to do this showing you how to use the tables, and you'll see that the result is the same no matter which way you decide to do it. Okay. Alright, so R represents the amount of each regular payment, which in this case is $100. I represents the interest rate per conversion period, so that's equal to 9% divided by 12, because interest is compounded monthly. And then n represents the number of payments. Okay, and it says right here it's 24. And type in equals 24. So let's follow the formula. It says R times parenthesis 1 minus parenthesis 1 plus I to the power of negative n divided by I. And we get $2,188.91. Okay. If you had decided to use the tables, R is still the same, N is still the same, but the table has I expressed as fractions, so you might want to think of it as 9% divided by 12, and 9/12 reduces to 3/4. So on the table you would look up 3/4% in row 24, n equal to 24. So let me find the table here and I'll show you how to locate that number for this part right here. Okay. Okay, here's the table. There's 3/4% right there. And if we look down right here in row 24, we see the number 21.88914614. Okay, so we take that number times R. So 100 times 21.88914614, and you see that no matter which method you decide to use, the result is the same. Now I would like to explain to you what this means. Okay? We found the present value. Okay? So this means that if you invested this amount right here, the $2,188.91, if you invested that much today for 2 years, such that 9% interest is compounded monthly, you would have the same accumulated amount as an annuity of 24 monthly payments of an amount of $100 each, compounded 9% monthly. Okay? I want to really show you what's going on here so that you understand what I just said. Okay? So let's see. At the end of period 1, remember this is an ordinary annuity, so the $100 payment is not going to occur until the end of the month. Therefore, the interest is 0 at the time. Okay? And at the end of month 1, we have $100. All right? Now, at the end of period 2, I'm going to set up a formula here so I don't have to count these out. I'm going to say cell A2 plus 1. Okay? At the end of period 2, we have earned interest on $100. So $100 times 9% compounded monthly. So we have 75 cents interest. At the end of period 2, we have also deposited another $100 payment. So really, at the end of period 2, we have the first $100 that we put in plus the interest, and then plus the second $100 that we put in. Okay? So at the end of period 2, we have $200.75. Okay? Let's do one more. At the end of period 3, we have accumulated interest on this amount. So take that times 9% divided by 12. Okay. We've made another $100 payment. And the accumulated amount was what we had prior to that, plus the interest, plus the third $100 payment. And this is at the end of period 3, this is how much is now in the account. Okay, keep doing this for 24 periods. And what I'm going to do is I'm going to copy this and drag this on down to not 24 because we have a row of titles up there, so to row 25. And we have $2,618.85. Okay, we had done the work and found the present value to be equal to $2,188.91. Okay. Let's find the future value of that, assuming that the interest rate is 9% compounded monthly. That would mean this amount times 1 plus 9% compounded monthly to the power of 24. Okay. We're off by a penny, but that's probably due to the rounding in the computer. Here's what we have verified. If you had a lump sum of $2,188.91 and you put it in an account that earns 9% compounded monthly, after 2 years you would have this much in an amount in the account. Okay? Or if you decided to set up an annuity such that you deposit $100 at the end of each month for 2 years in an account that earns 9% compounded monthly, you end up with $2,618.85. So that's what I meant earlier. Okay, so if you invested this as a lump sum or decided to set up an annuity, at the end of 2 years you end up with the same amount of money. This is what we have verified with this work. Okay, let's look at one more example. Okay, read the problem. Alright, so a down payment of $2,000 was made, and the purchaser is going to continue paying $200 per month. So that is a type of annuity. Okay? So R stands for the regular payment, which is $200. I stands for the interest rate per conversion period, so that's 12% divided by 12 since interest is compounded monthly. And N stands for the total number of payments, which is 36. All right, so let's follow the formula and find the present value of that. Okay, so that would be R times parenthesis 1 minus parenthesis 1 plus I to the power of negative n, close parenthesis twice, divided by I. Okay, so the present value is $6,021.50. Now, if you had decided to use the tables, R is still 200, N is still 36, but the tables expresses I in terms of fractions, so you want to think of this as 12% divided by 12, which is equal to 1%. Okay, so you will look up on the table, you will look in the column that says 1%, and you'll scroll down to row 36. Let me find that table for you. There's the 1% column. Scroll down to n equal to 36. There it is. Down at the bottom, it's 30.10750504. And that's the number that we're going to multiply times r. So we're going to take r times that number that we found on the table, 30.10750504. And you see the result is the same. Okay? That's the present value. The original cost of the automobile, remember he already put $2,000 down on it before this agreement began. So add $2,000 to the present value. Okay? So the original cost of the automobile is $8,021.50. Okay? Now, interest. Okay. He paid $200 for 36 months. Okay? And then, if you subtract the present value from that, that tells you how much interest he ended up paying by taking this loan agreement. So, okay? I hope this helps, and I think you're ready to tackle some problems now. And please remember that if you're stuck on something, to post your question on the discussion board.